According to Italian law, I am a professor of bioengineering at Polytechnic of Milan, but by myself, I am an academic scientist because I am a lifelong learning student. Okay, I like to start from the root of the problem. So we start any voyage, any journey starts anyway with the first step. So we start from the beginning. Horror vacui. Horror vacui may have had an impact, consciously or unconsciously, a dread for emptiness from nature to primeval man. Overwhelmed by an excess of emptiness, forced to live in a world not yet filled up with signs, symbols, and meanings. In visual arts, horror vacui is horror of empty spaces, especially in aversion to empty spaces in artistic design. In ancient Greece, during the geometric age, horror vacui was considered a stylistic element of all art, the same of Arabic Islamic art from ancient times to the present. More recently, the concept of horror vacui in art was associated with Italian-born critic of art and literature, Italian critic of art, Mario Praz, who used the term to describe the suffocating atmosphere and clutter of interior design in the Victorian age. On the other hand, the current proliferation of new sciences extends the powers of senses and thought, but their rigorous techniques and technical language hamper direct communication. The common field of knowledge becomes a diminishing fraction of the total store, stuffed by an overwhelming excess of irrelevant design and symbols, and the horizons of accumulating ignorance are expanding faster than any person can keep up with. It's happening something like it already happened in the mass media arena, where the mass mediatic scam has totally overwhelmed our way to communicate by the incessant growth of irrelevant information, visual and auditive requests. Laymen can find themselves in an horror-plane situation, totally unable to discriminate the difference between an open-eyes encoding format rich message and a random jumble of signs. And then you discover later why I emphasized this line. So, horror vacui or horror planning. As a matter of fact, our unconscious background is pervaded with an ancestral, primeval, cosmic, and abysmal dread for both situations. A dread that our current existential level is amplifying to upper levels of global confusion. Horror vacui and horror planning are two fundamental concepts to human beings, and their deep meaning can be extended to many different disciplines areas, like art, literature, sociology, science, etc. As an example, in the scientific and bioengineering areas, they can create operative reflection from experimental verification for the new never-ending human knowledge advancement without forgetting to remember our fundamental component, life. So, systemic reference paradigm. You know, just William Byers used the term conceptual system. They are the same. I mean, you can call them paradigms or conceptual systems. They are just tools for our mind to grasp reality in a more synthetic way. Okay? But I like to show you just little examples starting from just sentences. You know, the first one is iron rust from disuse. Stagnant water loses its purity, then in cold weather becomes frozen. Even so does inaction set the vigor of the mind. Who said that? I give you a little help. Second phrase, same person. The water you touch in river is the last of that which has passed, and the first of that which is coming. Thus it is with time present. Who said that? A fatherly law. There is no certainty in sciences where one of the mathematical sciences cannot be applied, or which are not in relation with these mathematics. Wow. Who? Leonardo da Vinci. Okay, and then I like to show those ones because was something that Leonardo grasped: intellect from emotion, intuitive mind, and natural inquiry method to inquire nature are born. Second example. Speak obscurely everyone knows how to do, but very few clear. Who said that? Galileo Galilei, the same guy who wrote this philosophy, is written this great book, I mean, The Universe, which stands continually, and I think that is a phrase that you heard already many times in different contexts, because it's widely known. And the third one is less known, and by experience his knowledge was reduced to diffidence. So that when asked how sounds were created, used to answer tolerantly that although he knew a few ways, he was sure that many more existed, which were not only unknown, but unimaginable. Still the same guy. And then, intellect without emotion, rational mind, and classic scientific method to inquire immanent reality are born. And so I give you these two examples because you have to compare these two methods, the natural one and the scientific one. Leonardo da Vinci versus Galileo Galilei. Or Newton, if you like. But Galileo had something more than Newton. I am Italian, so I have to say that. You know? So, objectivity, traditional definition by the scientific method, objectivity as a scientific dogma. But as already many and Gary just underlined, objectivity has a double meaning. But as everything has at least two meanings, because, as you'll see later, we have to take, if we like just a more significant definition of the situation, we need always an inside point of view, an outside point of view. And so, objectivity as a scientific dogma is something that is applied by the first paradigm, scientific paradigm, but objectivity has to be intended as objectivity as an objective reality that everybody can perceive, or objectivity as impersonal point of view. So, inside point of view, outside point of view, you see? Impersonality is outside point of view, is the reality that everybody can experience by himself, and by a magic point of view, everybody sees the same thing. Isn't that amazing? And so, at the other point of view, the personal, the subjective point of view, but that is has to be an objective, and so has to become impersonal. You have to take away your personal influences. Okay? Is that clear? Good. So we can proceed as now that we have made this kind of precise definition according to a classic scientific point of view. Observer is a pure spectator, in the sense that, like going to a movie. So you see reality, and you just, as an observer, you get all the movie, and you are there just watching what is happening. That was the assumption of the first scientific framework. And so, pure spectator, you have some kind of natural experiment going on, and then you receive some kind of things that you assume is information, but according to modern systemic point of view, is not information at all, because you are even unable to estimate the transfer function of that connection. Is that amazing? And so, classic single domain channel transfer function approach, Shannon passive information channel, from information theory we can immediately make a systemic example of this situation with the Shannon information channel where you have an input, then you have a channel, a passive transfer channel, and then you have your output. Okay? That was the Shannon approach, in the sense that you will see later. It gives you some kind of advantage, but without telling you, you pay a big price for that. And we'll see later what we pay. And so that was just the beginning, where by definition the observer was outside the experiment. And so, with that kind of definition, a full theory was developed, ergodic theory, where, by definition, the observer is not perturbing the system that is evolving, by definition. But that was not enough, because in the 20s or 30s, I mean, advanced researchers just realized that that was a framework a little weak for more sophisticated experimentation. And after the 50s, when more sophisticated tools were available, like the laser, they developed more sophisticated research tools like the pulse-controlled perturbative approach. And in the sense that now, with the laser, we are able to perturb the system and then immediately to capture the result of that perturbation. And that was a technique that was called pump and probe technique. You pump energy and then you probe the result of that pumping of energy into your system. And that was a technique that allows to start to get a big step in the research arena, because it allowed to get information from non-linear behavior of your system. And so all the techniques were developed to pass from a pure spectator situation to the ergodic observer situation. That was a little better, because now we are able to estimate the transfer function between source and destination. You see the difference from the slide. You see the upper slide has a question mark in the transfer function. On this lower part of the slide, you have an S, that is the complex variable of the transfer function that you are able to estimate. And so there are 4 keys to a science. They has to be based on observation shareable. Well, I anticipate some kind of concept like shareable data, which are independent of any subject perspective, based on mathematical measuring system, universally applicable, subject to empirical testing to confirm the observation, and as a result, the application of science must be valid and reliable. Okay? This is the classic scientific approach used till today. But then you can even map this kind of approach with a refinement cycle, where you start from the top, make observation, think of interesting questions, formulate a hypothesis, develop testable prediction, gather data to test prediction. If your prediction are not what you think, then you have to a recursive internal cycle to refine, understand, and reject hypothesis, develop testable prediction, go further to develop general theories, and so you close the cycle. And this is something that is routinely used in all research laboratories today. And so, using this kind of approach, now, today, I think if you check on many different books, and then on Wikipedia, that you know is not a scientific reliable source of information, you can discover that you can refer to something like the latest reading that I had listed something like 76 different reference framework for scientific research. And so, if you group all those kind of framework, just to have a clear idea, then you can arrive at something like this one. you have the naturalistic DaVincian approach, and then you see that now the naturalistic for Da Vinci was intended as a research world where you got a space-time representation. Space-time. You see, space per time. Or multiply time in English, per is a division. And then you have the relativistic Galilean, and then in that approach, the time is absolute and space is relative. So the Galilean approach moved to relativity space, but then made a split between space and time, losing information without realizing it. And then you have the reductionist positivists, and so I think that you all know, or you recognize the date, 1687, Principia Mathematica by Newton, and so time is absolute and space is absolute. We go back from a space point of view, and then we arrive to relativistic Einsteinian, where we again talk about space-time together. Okay? But we talk about space-time at theoretical level. When you implement relativistic on machines, then you get space-time splitting again, lose information without realizing it. Then a big change. You know, the first four ones can be referred as classical physics, and then we start from the 1920s to the quantum physics approach. And then quantum stochastic was the first one, the Copenhagen interpretation is Bohr, Werner, Heisenberg. And then you see that now with quantum stochastic you are able to have an estimation function of a space-time. Estimating function of a function of space-time. An indirect feeling of that. But anyway, better than the previous one. Then we have quantum casual, and then we have again space-time, but this time, for the first time, with an open system view. And that was the Broglie-Bohm theory interpretation, and then it's something really amazing for that time. I mean, I put that 1992 because it's just the latest revision, but they started much earlier than that. And then the quantum transactional, again open system, by John Kramer and Kastner. And the latest one, the latest entry, quantum relational, that is again open system, the relational quantum mechanics interpretation by Robelli and Frassen and by Birbon. Again, you see, it's up to you, your choice. But the point is that you are free to choose any paradigm you like between those are just grouping of many different paradigms. You know, just in one line of these, you can find many different flavors of that kind of approach. But the interesting point is that when you have a round table by physicists, they sit there and they start talking about problems. And then, okay, well, this one is something to remember that the quantum, the big difference with the quantum approach with the classic approach is that from the quantum approaches you play correctly, that your classic interpretation can emerge nicely, okay, with no problems. But the interesting thing is that, again, a round table physicist, then you get immediately paradigmatic confusion. Because they start talking, but nobody declares which paradigm is he referring to. And so a lot of resources wasted. And so paradigmatic confusion occurs when incompatible epistemological assumptions are inadvertently mixed in explanation and practice. And that's a big issue in current science, in any discipline. Because I just use physics because it's just some kind of basic reference for all the other disciplines. But again, you can say that you have the same situation in many other disciplines. Okay, this is our current situation. So lucky we are. And then, just for our discussion, let's try to figure out a basic operative reference scenario. And so we have a natural system. I beg your pardon because I represent a natural system with the corners, because natural systems don't have corners, they don't know geometry. It's a human interpretation of natural system. And then we have a systemic interpretation and encoding of the situation. And then we have a formal system description of the situation. And then from that, we can have an operative interpretation, a decoding, and then an application finally to the physical system, to the natural system. As you saw, this kind of approach is something that is met, you see from the figures there, is met on the healthcare application arena, because just to show how the standard usual medical approach is always late. Is in the sense that if you start from the natural system, you get information, you compare those information with the reference system, and then you think about something to be applied to the natural system. When you have your solution to be applied to the natural system is on a different state. You are always late. Okay? Think about that when you heal. Okay, and so this is our reference scenario. You can apply this one to anything else, because as you can see, I numbered the different parts. So you see 1 for the natural system, 2 for the system interpretation, 3 for the formal system, 4 for the operative interpretation, and then you can map that from a systemic point of view to something more impersonal than that. And as you see, the numbers are referring to the same parts of the previous figure, but this is the usual systemic presentation of the same problem. Okay? Can you imagine? But now you have online this kind of my slides, so you can immediately check to be sure that you interpret things in the right way. And so, linear feedback example, prognosis. Now you know the value of medical prognosis, if you understood the delay that is implied by the usual approach. An approach that, if is based in this way, is always late, by definition. But the problem is that, and that what finally, until the 60s or the 70s, because we apply this kind of knowledge to linear system only. In fact, this kind of diagram is a diagram for a linear system only. If you like to control a linear system with a linear feedback, this is the diagram. So it's a simple situation. In fact, system control theory developed a lot and got a lot of success. We were able to put a man on the moon. We had to have a lot of other goals achieved. But again, with the big assumption that our systems were linear. The reality is that when we try to map that model to a multi-scale system like a real one, that is composed by particles, atoms, molecules, cells, organisms, ecosystem, Earth, universe, you immediately realize that the linear system assumption is not valid any longer. An example, for instance, just my area by engineering, you start from amino acids, then you have collagen molecule, collagen fibril, collagen fiber, to arrive to a tissue. Can you imagine? Or for a nervous system, you start from molecules, synapses, neurons, network, mass system, central nervous system. And then we just make models of each subparts, and you see on the right side, and we try to make mathematical models of those parts and try to put everything together And the final result is that we have just to compromise between structure and function, and so space and time again. And then the final result is something like that. This is a framework for simulation, for multi-scale numerical simulation. You start from quantum mechanics model, then you have a force field, then you get a water model, a coarse-grained force field, then you have a mesoscopic model, constitutive relation, and finally you get the continuum model. Okay? But the point is that all these models are just solved in an horizontal way. So there is no vertical connection. The vertical connection will be supplied by scientists, by researchers, currently. So the final model, this kind of approach, personally, I don't want that you go around saying this kind of thing, but I can tell you that is sounds like, I don't know if you saw the movie Frankenstein approach. Okay? This is something similar to that. The root of the problem of multi-scale system modeling, a small-scale system in focus, and a large-scale system. And okay, and so there is always a gray area that we are unable to manage in a right way, and so we have a big loss of information in the gray area. So, a complex system, this is something that, just to give you an idea, you remember the first diagram for a linear system, then this is a diagram for a nonlinear feedback system. A little different, huh? I have no time to go into detail of that, but just to give you a flavor that the situation is quite different, okay? And so, welcome to complex system reality. And so we get many relationships, and then again, if we like to go deeper, much more than that. But the final thing is that all this kind of complexity for our system just boils down to 4 asymptotic regimes that we can find. It is stationary, equilibrium, periodic, quasi-periodic, or chaotic. 4 different regimes only. But the difficulty is just to be able to predict, according to parameter variation, which one of them will be just reached by the asymptotic behavior. And so this is the kind of multi-system we like to study right now, that is, you see, just a little goal. I'm joking, because you see there we have the universe. But if we like to get further, I think that we have to develop tools to be able to model the kind of things in the right way. There is the technology, we have the tools, but we have the wrong scientific approach, because we still use the Newtonian approach. That's the real problem. And this is the test. What you read there? Light is? Wave. We see particle. We see waves. Both. The right approach is both. That's just a little example to give you the quantum mechanics understanding. That is something more than the classical mechanics. Okay? And so, if you start thinking that way, you get an information evolutive scale, but from a data point of view, that I call, to be honest, I call that by the Bateson Institute, International Bateson Institute, I call that cold data. Cold data versus warm data. The transition from cold data to warm data is when you pass from knowledge to wisdom. Okay? And then I use just a little example, and then just to give you
warm data?
Yeah, it's up to you, but I just, my little question is this the answer spinning right or left?
I know, I can see it both ways.
Why? But again, it's up to you. If you fix your mind and you start switching, you can turn the way the dance is spinning. Okay, well, this is something might be difficult if you are not read a little, but I give you an easier example. Which way is the train going? And I give you this example with the on the left side, and then I give you the same example on the right side, just to give you a possibility to check your peripheral system. Which one of them you see you make less effort to change the direction? That is your dominant part. Okay, so you see, even to give graphic messages, you have to be aware that there is a dominant part. But why we get this kind of behavior is just a matter of our senses that are not perfect, or there is something more there. Well, the human condition, and I have 2 minutes or something. Okay. As a matter of fact, the classical instrumentation noise discrimination problem is still faced by the single domain channel transfer function concept, Shannon noises channel, till today. Starting from classic Shannon information theory concept and then applying traditional perturbation computational model under either additive or multiplicative perturbation hypothesis. In general, HX, called Shannon entropy, is the average unpredictability of a random variable which is equivalent to its information concept. This is the definition. The concept was introduced by Claude Shannon, already cited, I think yesterday or this morning, in 1948, a paper in Mathematical Theory of Communication. But the basic concept is that HX is just a tool that helps us to disambiguate a situation like the first one I showed you. Okay? It's a mathematical tool. Yeah, you to do a few computation, a computer can do for you to help you, and then from that result you have your final answer. Okay. But the point is that Shannon entropy provides an absolute limit on the best possible losses and encoding or compression of any communication, assuming that the communication may be represented as a sequence of independent and identically distributed random variables. Emphasize, sequence of independent and identical distributed random variables. Like saying Gary, if I say Gary, G is independent from A, R is independent from the second R, Y is independent from the previous just characters. I mean, can you believe that? That's the approach. I mean, I can use if I get some kind of some convenience, but this is the price that we have to pay. We have to pay the price that we are unable to disambiguate the situation that I showed you before. And in 2004, University of Michigan physicists Newman and Lachman, biologists Lachman and Moore, applied Shannon approach to electromagnetic transmission. Specifically, they show that if electromagnetic radiation is used as a transmission medium, the most information efficient encoding format for a given message is indistinguishable from black body radiation. This is a little technical, I know, but this is the reality. So paradoxically, if you don't know the code used for the message, you can tell the difference between an information message and a random jumble of letters, noise, and unstructured information concept. In the sense that we are unable to discriminate an optimal encoded message from noise. But not as a humans, certainly as a humans, but even worse, as machines. Currently designed machines. I show you just a little example, and I close with this one, the second one that is just related. Just a little question. Which one of them is more random for you?
Which one is more?
Random. Random. Okay? It's up to you. So I think that if you are not trained, I mean, even if you're trained, you need help from Shannon. So Shannon entropy is a tool, is a number that tells you that is a number between 0 and 1. The closest to 1 the more random your data. Okay? So, please, compute Shannon for entropy for us, and then we get this kind of situation for the upper one. Oh, you see H1, H2, H3 is in simple precision, double precision, multiple precision, because when you have to deal with machines, you have to specify the precision of your output that you like, and that's something that we have to go back because it's something so important and nobody talks about that. And so it's the same for the last one, for the lowest one. And so, which one now is more random according to Shannon entropy? We saw that the closest to one is the more random. So, there you see that the lower one, as H1 is 1.000 to H2 1.000, it's just the theoretical limit for random variable. So, that is the most one because the top one get lower values for Shannon entropy. This is the machine, but the reality is that that's not true. Because the lower one was deterministic computing. That's the trick. So, just to give you an example of objectivity and subjectivity. If we don't solve this problem, we are unable to solve the objectivity-subjectivity problem. Okay? Thank you.
Thank you. Thank you.